Alright, in this video we're going to take a closer look at the import options and things surrounding the import capability of the InStep Studio 3D application. If you've watched the general introduction, you'll have a basic idea of the different things you can do within InStep, the different tabs and general workflow, so I'm not going to cover that in too much detail here. This will be pretty much focused just on import and the general things you can do. So the easiest thing you can do is you can actually drag and drop a file directly into here. So if I bring in our monkey, just drag it in and drop it, comes in. This is Susanna, I shouldn't say the monkey. Fairly straightforward. If you have a file, you're not quite sure what the different data sets look like, you can always toggle through edges, vertices and facets with Alt F for facets, so you can turn those on and off. Alt E for edges, turn those on and off, vertices on and off, and whatever combination of that you prefer. I generally like to have facets and edges visible, that way I can see if there's anything going on that's kind of crazy that shouldn't be there. But you can toggle that around and you can modify that. So we could have just as easily gone through open, import that shape from here. Does exactly the same thing. We see it's got 13,924 features. So in this case, features is just triangles, and we get that indication down here where it says all tris or all triangles. And from the same pop-up, you also see the number of bodies. B is 1, and the number of facets. So as this changes, as you edit it and make changes, that number should generally stay updated. We also have our units set. So right now this is set to millimeters, and if you want to get an idea of just how much this data occupies, we can go to the info, and then we see there's just body 0, it's just the name it's associated with it. We can see the area, and this is in units of millimeters, so this would be 10.384 square millimeters, I guess. Feature count, we have the maximum min point, so this is the bounding box that's aligned with the XYZ axes. What point on the lowest XYZ and the highest XYZ is. So it's the max and the min point. And then that's basically the range, is just this number minus this number and so on. It also calculates volume for you, so that's kind of a new feature in the 3.1 application. Previously it would just give you area, now we also have volume. Some people kind of like that idea, so we figured out how to do that. None of these are editable, so this is just information, but it's often a quick check to go, well, I know my original is so and so many millimeters or inches or feet or yards or whatever number you prefer, and then compare it and say, well, do those match? Is it vastly different? If it is very different, you can go in and resize. So let's take a look at this. Remember we have, about 2 millimeters in each direction. So in a physical size, that's very small. We might actually realize that we didn't mean to say that the data is in millimeters, but it's actually in inches, right? So again, we see these numbers displayed here, and we still may want to keep millimeters as the target, but for some reason the import data is in, say, meters, right? So in the original file where it says 1.2, that may actually mean 1.2 meters, not 1.2 millimeters. So we can just go and click on meters as the loaded data is, and then you see up here it all updates. So it now means that the X extent would be 2.66 times 10 to the 3 millimeters, so 2.6 or 2.7 meters. It might be that it was in centimeters, right? So that changes again, so it goes 26 millimeters. Or over here in inches and feet. So if the original data was stored in the file as inches, but we want to use millimeters, you click on this and it'll recalculate. If for example, we say, no, this was actually millimeters, so it is a really small model, but we would rather use a different unit, so we want to have it all in meters. We can change our work units to be meters, which will change this down here if we hit apply, and then it'll say what the actual size is. So you have to have an understanding of what the data is meant to represent in order to make correct choices. The bottom section relates to what the data was stored at in the file, and this up here represents what you want to work with. I should point out that millimeters, centimeters, and meters are the most standard units. In fact, I would generally recommend you keep it to millimeters and make a change here to apply any kind of specific scaling. The reason I say that is that most step files, and presumably the goal of this is to export as a step file, they like millimeters. They also generally like centimeters or meters, but they don't really like inches or feet. Even if that's the unit you want to work with, say you're using SolidWorks or a Libre or something like that, it's a lot easier to import in millimeters because your CAD application will understand the units and then convert it into what you actually want to work with. Some applications don't understand inches or feet, so that's just something to keep in mind. So the other thing we can do is we can just do some other scale. So let's say we look at all these and go, no, that's not right, that's not right, that's not right, inches, feet, none of this makes sense, but I know what it should be. You can apply the scale directly here. Let's say we wanted to just factor of 10, right? So clicking on centimeters, keeping it as millimeters, we'll scale it by a factor of 10. We can do a quick preview and we see, oh yeah, this now matches because this still is 1 millimeter. I'll take that back. Yes, correct. This is 1 millimeter. So if we turn the facets off, we can see each arm of this triad represents 1 unit of whatever we select here. Okay, so we know X is 2.66. X is always red. You can remember that by RGB, red, green, blue, X, Y, Z. So we have 1 millimeter here, and we probably have another millimeter over here, and then a little bit for the ear. So 2.6 makes sense, okay? So we can then apply, or we can just cancel out in this case because we're not making any changes. But that's the resize option. The align tool is a little different. So resizing is just scaling bigger, smaller. Aligning allows us to modify the orientation of the data, which includes offsetting along the X, Y, and Z coordinates, but also rotating. When we open up the Align tool, the first thing we see is this bounding box, which seems to be at an angle relative to the origin of the data, and that's actually very consciously designed that way. What it does is it calculates the minimum box that this would fit in, and the minimum box isn't always oriented with the original data. In some cases this can be useful for especially scan data, which may or may not actually been lying on a table when it was scanned, so recreating that layout is often desirable. If we don't want that, we can actually just go in and remove this. In this case it's just a rotation around X. So we can just go ahead and remove that, set that to 0, and you see a little animation. It orients it back to matching the origin. Now in this case, if let's say we wanted to import a second one of these shapes that is offset along the X, for example. Right now the origin here is at minus 1.33. So the easiest for this scenario would be to shift this along X by a certain number. Now we know it goes minus 1.33 to plus 1.33. So if you wanted one exactly on the other side, we would just make this positive. So we see the preview here. If this is what we want, and in this case the very simple alignment, we just click apply. It regenerates and updates. Now you see the origin is located over here. Now we can go in and do some more complicated stuff with this. So in this scenario, it's a very organic shape. There's no flat surfaces, but we can go in and pick an X, Y, Y, Z, or different surface to align this to, if we wanted a flat surface as a reference. So we pick that, and then pick a suitable triangle to set it. I should point out the result is not 100% accurate just because of the way the data can sometimes be manipulated. Generally, it'll be within a thousandth or a millionth of whatever units you have set. But they can be just a very, very small discrepancy, especially if the source data isn't in itself perfectly flat, which is usually the issue there. In a scenario like this, we may actually want to just say, well, no, we don't like this bounding box. We also don't like the original one. But instead, we want to, for example, align the z-axis exactly aligned with this edge. So we can go in here and actually pick which axis we want to align that to. So we go in there, pops up the line selector. And there are a number of different options here. This is something we'll cover later on and over the course of different tools. But we just be picking the existing edge option. So do existing edge, and here are the two coordinate points that an existing edge is defined by. We start this by selecting the edge. So this is the select start point, and then in here you see the edge is actually being highlighted as we hover over them. So let's say we pick this one, click here. Now it says, okay, it's these 2 points, and we can kind of tell that those are actually the ones we're looking for. Click OK, and then I'll zoom out a little bit here. The z-axis actually becomes aligned with this. Internally calculates the best possible match for this. This is actually not as simple as it sounds. The main reason is we're not using a local coordinate system, in the sense that we're defining an x, y, and z point with an origin, and all those points must be an orthogonal coordinate system. We're just defining one axis, and we're trying to adjust the origin to match that axis for whatever we picked. So with the y, if we first pick the z-axis and then the y and then the x, one of them always has to be different than what we picked, unless they are perfectly aligned in that way. One last thing with this here is, when, let's say, we cancel out and we go back in, originally the coordinate origin is located in this corner, and up here we can actually pick different ones. Now obviously this doesn't, you think this point would actually be this one, but it's just a matter of how you orient it. You can always make it be that point, right? So right now it is actually that point. So if we click here, it would be down there, right? So we have those options to pick different coordinate axes. And then let's say we go back to the first one, we can also spin it. So if we wanted to actually have that spun, we can just click +90 to make that spin around. And the calculations are internally done to match that transformation. Once we're happy with that, we click apply, and then we're left with whatever our last setting was. So that's the align tool that we want to use there. But that gives us options to play around with, orienting and setting it to a more desirable orientation. That's the align tool. The FE tool, we can have a separate video on this specifically. The idea is you can take these surfaces and actually say and actually define them as facets of a finite element model. So these will be triangular elements. We could do stress analysis on that and similar. So one last thing here, and that's probably a big one. The import tool also consists of the option to bring in point clouds, or we can also insert second data into the same data set. Generally, I recommend against using this. It's a lot easier to work with one body at a time than to try and have multiple bodies, and distinguishing between operations that affect all and operations that just affect a few. So generally I recommend not bringing in multiple bodies, but the option is there. So you could import another body and add it to this data set, and I'm just going to very quickly show what that could look like. So this is just a multi-body item. I'm going to try and find yeah, there we go. So I turned the facets off to see through these, just to see what the origin is, and you can see that this body is now basically obstructed, but all the bodies are in here, and this would form one solid data set. So we could export it to one file and it would contain all the geometry in there. Again, I don't recommend doing that too much. In fact, I recommend the opposite. I recommend that you take bodies that contain multiples, split them up and work with them one at a time, and that's something we're going to show in a different video, where we actually cover the bodies options and things that fall under here. So in this case we just split the data up, and that'll give us a preview. We see all the different items, and then we can also go in here. For example, let's say for some reason this came in this way and want to keep just the monkey. We select the monkey, turns red, right click in it, and then we do delete all others. This should say delete all others. Alright, so we're left with just our monkey again. One additional item here, and I will quickly show the F2FE tool, but we can also bring in point clouds. Point clouds are a little special. Usually they're generated by 3D scanners or a CMM or something like that, and most of those machines will come with their own software. The software that comes with those machines are often the best software to use for that specific data set. So I strongly recommend against relying on this application for point cloud data. In fact, if you use MeshLab, which is a free application, that is a very good tool, and I would recommend that over this one. Nevertheless, there are some point cloud scenarios where this may come in, and for that reason the point cloud import option is there. So point clouds can be brought in just like any other file, but there is extra work to it. So we're going to take a quick look at one example here just to give you an idea of what's going on. So we click point clouds, and I have this sample file. The other monkey file is basically just an export of that, but we're going to look at the fighter XYZ file set. This is for Star Wars fans, this is going to be an interesting one. It's a Naboo fighter, I believe. It comes in, and it's important to note that it says number of points without normals. Okay, the without is important because it means we don't actually have enough data to generate surfaces from this. Each point needs to be defined as which side faces in, which side faces out. All the algorithms rely on this. In the future there will be a new algorithm that's sort of in the works now that will be able to distinguish points directly, so there won't be any additional pre-processing required, but for now we actually do need the normals. The three algorithms built in here are actually external applications that the InStep Studio application interacts with and generates the command lines for it, but all of these require normal definitions for each of the points. So for something like this, I personally prefer the LS plane option. We see down here it's got normals estimation tool built in. LS plane just means a least square plane, so we look at a number of neighbors, in this case just preset to 10, takes 10 points, generates a plane through them, and then looks at neighboring planes to figure out which side should most likely be inside or out, and kind of propagates that data through the entire body. We have other options too. The chunky algorithm is sort of hit and miss. Barycenter is essentially intended for something like a sphere. Most often that won't work, that won't be good enough. If you have a scan of a surface and it's just a surface from one direction, you can often just define the XYZ direction, and that will be good enough. If it's in a separate file, perfect, just import that file. But then there's these two down here, the ls plane and ls sphere. So there's least square plane, least square sphere. The plane is a little bit more robust, but they both work on the same principle. It's a least square fitting of a plane to data set. 10 probably works. We'll keep it, make it just a little bit smaller, let's say 8. And with that set, that's all we need to estimate the normals. So we're going to click estimate normals. This can take a little bit. This is a relatively small sample of 183,000 or 184,000 points. So a few seconds in, let's see what comes up. Okay, so the display generally will switch over to points and normals. You can set that down here. But by sort of looking at this, we see that most of the points are probably in the right direction. I think if a few of them are the wrong direction, the algorithms are usually generally quite robust, and that will still work. But this one actually looks like the plane method result in good data. So we're going to leave that here. We're going to keep the smooth sign distance option, which is partially internal algorithm. It looks at a point and tries to determine if there's if the point is internal or not based on the signed distance to the surface. I'm going to leave these parameters the same. I don't actually know what all of these mean, but I do know that, for example, max memory, if you set it to a number, it'll try and cap it to there. If you leave it at 0, it will just use whatever it needs, and generally these are quite efficient. Changing degree, changing depth, things like that may have an effect, and I recommend it's just one of those things you kind of play with, or look online for smooth sign distance. You know, for example, the bi-Laplacian weight, you know, figure out what that means, or play with it and see what the results are. Try this with smaller sample sets, like this is a good one. If I'm going to go ahead and do a preview on this, I'm going to click preview surface, and that will actually apply the algorithm to the data set. And once it completes, the display changes, just like we see here. This is in edge mode right now. If we turn on the facets, so Alt and F, we can investigate the data. Yeah, and this actually looks really good. So this is a good conversion from just points to surfaces. We can turn edges off, we can turn the vertices off. Anyone that hasn't seen the first tutorial, we can visualize facets with Alt and F, visualize edges Alt and E, and vertices with Alt and V. And it just toggles on and off. So Alt V turns those off, Alt E turns edges back on, and it gives us a good view. Anyone that looks at this area and says, well, what's going on? This is all crinkled. That's just the display method shows us flat shading for the facets. Some other applications may visually smooth this out, but that's not helpful. So the default is to have flat faceted display. So with that shown, this will actually be a good data set. So we're going to go ahead and apply, and that will take that preview data and turn it into the geometry that would essentially be in an STL file or an OBJ file. Now, this is generally fine. We see that these triangles that define the surface are actually quite uneven. So I do want to switch over to the FE tool. So let's say, for example, we were to do a fluid simulation of this body to see how good it is or anything like that. We may want to directly generate surface elements within InStep, and that's what this tool is primarily for. But in this case, a lot of these triangles would be really bad shaped, and a lot of issues would come up during the simulation. I will show a quick part of the bodies tab, just like I did before. We have a tool in here that's the remesh tool. So if we click this, we have the option of picking factors iterations. All of this will be covered in more details, but we can squeeze the factor a little bit smaller, and we can increase the iterations. Factor means how much can each edge or vertex, each of the vertices move per iterations. So in a perfect case, we keep this at a very small number and this one at a very large number, but we want to keep this efficient. So we'll make this 0.2 and 10. Different geometries and different meshes will benefit from other numbers, but here we're going to use that. Now, before we hit preview, one important thing here is the length option by default is just set to value. It's important that you make sure that the edges that you want to modify through the remeshing tool actually are what you intend them to be. So the idea is it's going to try and make it similar across the entire body. If you click average edge, max, min edge, and then switch to value, it'll show you what that number is. So average edge is this, minimum edge presets it to this value, maximum edge to this value. So for something like this, if you want to get a quick view, maybe consider maximum edge and then a little bit in between. So let's say 1.0, and we'll set at 0.2 and 10, like I said, and then we'll do a preview, relatively quick at this size, and we see now there's a fairly uniform number of uniform shaped triangles. We can go bigger, we can go smaller, so the remeshing of this will affect that. So if we go, we can look at 2.0. It's very quick. It's a very coarse mesh. If we then start going smaller, so let's do 0.5, so it'll take a little longer, we'll see that the mesh starts getting finer and finer based on what we set this to. So it goes both bigger and smaller. And it'll try and approximate the original mesh. Now, on a quick look, you can see these sections here that don't look very good. So this wouldn't be good mesh. The way we get rid of these is by increasing the number of iterations or making the factor a little bit higher. So I'm gonna go slightly higher factor. So say 0.4. Going to do preview on that again, same number of iterations as before, and we'll see if that gets rid of these skewed facets here. And yeah, so most of them got rid of. We can play this a little bit more and probably end up with 20 or something, but for the purpose of this, we actually now have a very nice clean mesh, and it would actually be with just a few more iterations of that, this would be a good source mesh as a sort of a general, I mean, I wouldn't necessarily use it for CFD, but as a general mesh, this would actually be quite useful. So we're going to go ahead and do the apply, so we can go back to the import tool just to walk through that a little bit in more detail. So the mesh is updated. We see that here. If we hover down here, now we see the number of facets, and we're at 173,000, so we're actually in fairly decent shape. The last thing I wanted to show was this 2FE. The clear button, I think, is apparent what it does. It just clears the data. To FE, clicking that brings up a new tab, so that kind of pops up here. And this is a separate tab we'll talk about in its own video. But the idea is that once we convert a triangular mesh or even a quadrilateral mesh into an FE format, the underlying data changes, and we then end up with new export functions that will come up once we actually work with these. So we can go ahead and say, well, the surface is fine, but now what I want to do is I want to end up with a true triangular mesh set from this data. So we just do the extract, and it'll go through and it'll remove the original data, and hence the color change helps with that a little bit. Yellow is just generally for the FE mesh. We are now left with a true two-dimensional FE mesh, and we have some extra options here that we'll cover. Under export, we now have the FEA button here, and that will just export this to an FEA style format, and that's all initiated through the 2FE. So it'll pop up this elements tab here that's otherwise not available. Only once we import data that's in a FEA or FE format, or convert as stereolithography, or in this case, a scanned data, does that come up. So with that being said, these are the items that are available directly from the import tab. There's a few other items, and those will be applicable through the settings. So we can go to application settings, and that brings up this entire box. I'm not going to cover this in too much detail. So most of these are self-explanatory. I mean, things like line size, line color. That's literally the color of this element. You can go in and change those things. One thing I wanted to mention, ask for large file scaling. If the imported data, it looks to be really, really small or really, really big, the application will generally say, hey, look, I think what he loaded is actually in the wrong units. Do you want to go in and change the units? And it'll pop up the dialog that's set for millimeters. The reason that's there is that in the past, people have been confused because they loaded data and it just showed up as a single point in their standard scaling. And the issue for that was that it was originally saved as, say, meters, and they were looking at it in millimeters. So there's a factor of 1,000 between. Things along those lines will generally need to be set. The application will ask usually, but you can also go ahead and directly turn that on or turn that off, depending what it's at. Your import units will, that's the default. You can set that here. You can set it from down there and then ask it to save. But that's in general some of the settings that you may want to take a look at in here. There's a lot of others. Most of them, if you click on them, you'll get a little dialog box down here that provide more information about what that setting does. And with that, we're gonna end this tutorial. There will be more coming along the way. These are designed to be fairly simple. We'll cover more detailed stuff. We'll do some walkthroughs later on. But for the most part, this is intended as a way to help you understand what the tools do and kind of give you an idea of what happens when you use them.